For this section, we're going to be talking all about how functions can be operated on the same way that variables and numbers can. Starting off with a fact that says functions can be added, subtracted, multiplied, and divided just like variables. And we introduce a notation for how each of those operations occurs. So for instance, if we have f of x plus g of x, in function notation that's written as f plus g of x. This is a simplified notation for what we're actually doing. Likewise, if we're subtracting f of x minus g of x, we have f minus g of x. It creates a new function when we do this. We can also have fg of x, which means we have f of x times g of x, and finally f over g of x, which means we have f of x divided by g of x. When we do this, as I said, we are creating a new function, which means that new function may have a different domain. So the domain may change. It is important to note the new domain as you go through these problems. So for instance, we have an example where we want to find f minus g of x given f of x equals 5x minus 4 and g of x equals 2x minus 3. So f minus g of x is equal to f of x minus g of x. And we know f of x is 5x minus 4, so we can substitute that into the problem and subtract g of x, which is 2x minus 3. With that, we are subtracting two polynomials now. So all we have to do is treat this like we've treated problems in the past. We'll distribute the negative. The first polynomial, nothing's going to happen to it since there's nothing outside of the parentheses. So we just have 5x minus 4 minus 2x when we distribute the negative, and then plus 3, as negative times negative 3 gives us positive 3. And when we combine our like terms, we're left with 5x minus 2x is 3x. Negative 4 plus 3 is minus 1. So f minus g of x is equal to 3x minus 1. And now we need to note what the new domain is. So when we're looking at these two functions, is there any value that causes division by 0 or a negative inside of a square root? For 5x minus 4, there isn't a single value that will cause either of those cases to happen. And for 2x minus 3, there is also not a single value that causes division by 0 or a negative inside of an even root, which means the domain is negative infinity to positive infinity. So our answer is f minus g of x equals 3x minus 1 with a domain of negative infinity to positive infinity. The next example, go ahead and take a moment, try this out. It's a bit trickier, but it follows the same process. See if you can't get through as much of this as you can. Okay, so trying this together, f over g of x. We said f over g of x is equal to f of x divided by g of x. Which means we're going to take f of x, which is x squared plus 2x plus 1, and divide it by x plus 1. And before we start simplifying anything, it is worth noting right now what domains we're dealing with. The domain of f of x is all real numbers. We cannot find a single number that causes division by 0 or that causes a negative inside of a square root. The domain of g of x is the same thing. There is not division by 0, there is not a negative inside of any even roots. But notice what we're dealing with. X squared plus 2x plus 1 over x plus 1. We are dividing by a polynomial. And there's a chance that this division could result in division by 0. So we need to make a note that x plus 1 needs to be set equal to 0 and solved. So we'll subtract 1 from each side. Oh, that's a typo, sorry. We'll subtract 1 from each side to get x equals negative 1, which means x cannot equal negative 1. In the domain of this function, f over g of x that we're looking for, the only catch is that x cannot equal negative 1. That's a new domain restriction that we did not have before, and it occurred because we introduced division into the problem. So whenever you do problems like this where you have division of two functions, you should always set the denominator, the bottom function, equal to 0 and solve to see if it causes division by 0. Okay, so continuing on from there, now that we know what domain we'll be dealing with, we need to simplify this. To simplify, we need to check if we can factor and cancel any common factors. This is one of our special factoring cases, but even if you don't realize that, you can just use guess and check or the middle out method. X squared plus 2x plus 1. We need two values that'll multiply to give us x squared, which are x and x. And then we need two values that multiply to give us positive 1 and add up to give us 2. That's positive 1 and positive 1. 1 times 1 is 1. 1 plus 1 is 2. And now notice we have a factor of x plus 1 in the top and bottom of our fraction that will now cancel off, leaving us with f over g of x is equal to just x plus 1. But, as we said earlier, we have a new domain where x cannot equal negative 1. It can equal anything else though, so remember we say we're going from negative infinity all the way till that negative 1. Union, we're going from negative 1 all the way to positive infinity. And this is our simplified answer. Continuing from there, now that we know how to add, subtract, multiply, divide functions, we can introduce compositions of functions. We say that a composition of functions is when one function is used as the domain of another. In other words, when you plug a function into another function. We notate this as fog of x, f of g of x. And we say that this is equal to what you get when you take your function f and you plug g of x in for every single x value. It's just like when you found f of 2 in the past, you'd plug 2 in for every x value. You're now plugging whatever g of x is in for every x value. It looks odd, but it's something you've done already. So, the process to find a composite function's domain says that we're going to find the inner function's domain. So in this case, we would find the domain of g of x. We would then find the domain of the composite function in its simplified form. In other words, whatever you're looking at when you find your simplified composite function, find the domain of what you see. You then take that inner function's domain and then the domain of what you see and intersect the two or combine them together, see what's common, and that is the domain of the entire composite function. So let's go ahead and give that a try. We want to find fog of x, f of g of x, given f of x equals 1 over x plus 2, and g of x equals 1 over x. Well, to find fog, that means we are taking g and plugging it into f. We are finding f of g of x. And we know g of x is 1 over x, so that means we're finding f of 1 over x. So that means everywhere you see x in your original function f, you're going to replace it with 1 over x. That's what finding fog means in this case. So that's going to give us 1 over x plus 2 is now going to be 1 over x plus 2. And now we just need to simplify this and find its domain. This is a complex rational expression, meaning there's a fraction inside of another fraction. So we need to find our least common denominator and multiply it to every term. Well, in this case, the least common denominator is just this x here. So we're going to multiply every term by an x to cancel out this fraction, which gives us 1 times x is x, over x times 1 over x. Those are reciprocals. When you multiply them together, you'll get 1, because the x's will cancel out, plus 2 times x is just 2x. So we have that fog of x is equal to x over 2x plus 1. It's generally a good idea to write your polynomials in order by exponent, and that's actually required in most cases when you're just dealing with a polynomial. But in this case, it's not a polynomial, it's a rational expression. It's still worth writing it in that order if you can. Now we need to find the domain. And remember, our domain says we first find the inner function's domain. The inner function in this case is g. So the domain of g is the domain of 1 over x. So we're going to check, is there anything that causes division by 0 or a negative inside of an even root for 1 over x? Well, the only thing that we can find here is what causes division by 0. We get that by setting x equal to 0, the denominator equal to 0, and that's already done for us. X cannot equal 0, otherwise you get division by 0. Now we do the same thing for the simplified function at the very end. So this x over 2x plus 1, or this x over 1 plus 2x, however you want to look at it, we're going to take this and check if there's anything that causes division by 0 or a negative inside of an even root. In this case, the only thing that will cause it is division by 0. If we took 2x plus 1 and set it equal to 0, we could subtract 1 from each side to get 2x equals negative 1. Dividing by 2, we get x equals negative 1/2, which means x cannot equal negative 1/2, otherwise we would have division by 0. So the domain of our composite function is all real numbers except 0 and negative 1/2. So writing that out in an interval, we start at negative infinity, we go till our smallest non-domain value, which is this negative 1/2 that occurs before 0. So negative infinity to negative 1/2. We put a parenthesis because negative 1/2 is not included. And now we put a union because we're going to be picking up at a new interval from negative 1/2 until our next break in the interval, which occurs at x equals 0, because x cannot equal 0. This isn't included, so we put a parenthesis, another union, and again we pick up at 0, and we continue until positive infinity, as there are no more gaps in our domain. So our simplified answer is f of g of x equals x over 2x plus 1, and it has a domain from negative infinity to negative 1/2, union negative 1/2 to 0, union 0 to infinity. So from here, I know these problems are pretty complicated, so I want you to take a moment, try one, and then we'll try it together. So we have g of f of x, GOF as it's sometimes referred to. We want to find GOF given f of x equals 2x plus 4 and g of x equals 1 over 2x. Go ahead and pause the video, give this a try. Okay, so trying this together, first thing we're going to do is, since we're finding g of f of x, that means we are going to take f of x and plug it into our function g. And we know f of x is 2x plus 4, so that means we're finding g of 2x plus 4. All right, and now from here, that means everywhere we see an x in our original function g, we're going to replace it with 2x plus 4. So that gives us 1 over 2 times x is now 2x plus 4. And simplifying this, we can just distribute that 2 to give us 1 over 4x plus 8. Remember, whenever you're dealing with one of these rational expressions, generally you want to leave it as factored as possible for your final answer. But when it's just a constant, you can feel free to distribute it. We only really care about factoring out variables like x's. So we get GOF, or g of f of x, is equal to 1 over 4x plus 8, or if you did factor it out, you could also say this is equal to 1 over 4 times the quantity of x plus 2. That would also be perfectly acceptable. And now from here, we find our domain. So remember, we first check the inner function. In this case, the inner function is f. What's the domain of 2x plus 4? Well, there isn't anything that causes division by 0, and there isn't anything that causes a negative inside of an even root, so the domain is all real numbers in that case. Now we check the domain of the final function, the final simplified problem. We have 1 over 4x plus 8. We could have division by 0. And we would get that by taking 4x plus 8 and setting that equal to 0. We'll subtract 8 from each side to get 4x equals negative 8. And then dividing each side by 4, we would get x equals -2, meaning x cannot equal -2. That is our only domain restriction. So what is our domain for Goff? It's all numbers except -2, which means -infinity to -2, parenthesis, and now we put a union because we need another interval, and we have -2 to positive infinity, parenthesis. And these are the answers to the problem. Goff, or g of f of x, is equal to 1 over 4x plus 8, and the domain is -infinity to -2, union -2 to infinity. From here, we have one last type of problem for this section, and that's how to read tables when you're finding compositions. So for this example, we have the following table, and we want to find f of g of 2 and g of f of 1. So starting with f of g of 2, that means we are finding f of g of 2 being plugged into our function g. So simplifying this, g of 2 means find your x value of 2, which is right here, and find the g value when x equals 2, which is 3. So f of g of 2 means we're really finding f of 3. And now f of 3, we go to an x value of 3, and f is equal to 2. So f of g of 2, or fog of 2, is equal to 2. Remember, we always want to be writing our function notation. Now, go ahead and take a moment. Using this table, try to find g of f of 1. Okay, so to find g of f of 1, we go to our x value of 1 because we're finding g of f of 1 being plugged into our function f. F of 1 means x equals 1, so our function when x equals 1 is equal to 4. So we're finding g of 4. And when x equals 4, g is equal to -8. So g of f of 1 is equal to -8.